All right, today we're going to get under the hood of Python, one of the most popular programming languages on the planet. We're going to explore its fundamental building blocks and see how they're used to solve some really complex engineering problems, especially in the automotive world.
It might seem like a huge leap, right? How can these abstract lines of code help build something as real and physical as a car? Well, the answer is simulation. And to simulate anything, you first need to describe it with data, and that is where Python just shines.
And this quote right here, this is the core idea we really need to wrap our heads around. You see, in a lot of other languages, you have to tell it ahead of time what kind of data you're storing. Python's different. Everything is an object, which just means it's a piece of data that also comes with its own built-in abilities. This simple shift is the secret sauce to Python's famous flexibility. So let's start right there, with that unique approach. Because if you understand this philosophy, you're already halfway to understanding how Python builds such powerful tools from such simple ideas. This is what people call dynamic typing. If you give a variable a number, boom, Python knows it's a number object. If you give it some text, it becomes a string object. You don't have to declare anything beforehand. It figures it out the moment you assign a value, which makes writing code feel so much more natural.
Okay, so if everything is an object, what kind of objects are we even talking about? Let's pop open Python's toolbox and take a look at the main players you'll be using to organize information. First up, you've got lists. Honestly, the best way to think about a list is like a shopping list. It's an ordered collection of things. And what's so cool is that you can mix and match whatever you want. Put a number next to some text, Python doesn't care. And here's the key. A list is mutable. It's a fancy word, but all it means is you can change it whenever you want. Add something, take something away, move stuff around. It's totally flexible. Next, we have the list's very close cousin, the tuple. It's also an ordered collection of items, but with one massive difference. It's immutable. Think of it as an unaltered list. Once you create a tuple, that's it. It's set in stone. You can't change it. So, why on earth would you want something you can't change? Well, lists are perfect for things you expect to change, like the current speeds of cars in our simulation. But tuples, they're for data that must never change by accident. Think of something critical like coordinates on a map. That unchangeability makes them incredibly reliable and safe.
And then we have dictionaries. Instead of storing things in a neat line, you store them as key-value pairs. It works just like a real dictionary. You have a word, the key, and you look it up to find its definition, the value. So here, the label vehicle speed points right to the number 120. It's a super fast way to get data when you know its name. We've seen how Python can organize groups of data. But to actually simulate a car's speed, we need to zoom in on one of the most fundamental objects of all, numbers, to see just how powerful these simple building blocks really are. Now this is where things get really, really cool. In a lot of other languages, numbers have a hard limit on how big they can get. If your calculation goes past that limit, your program can just break. Python, on the other hand, it basically has no limit. And that is an absolute game changer for complex math. I mean, to put that into perspective, Python can handle a single number with up to 36,000 digits. That's just wild. You can imagine why this is such a huge deal for anyone in science or data analysis who's dealing with massive calculations. The flexibility is just incredible. And doing math is about as easy as it gets. You use the symbols you'd expect, a plus sign for adding, an asterisk for multiplying, and for something a little fancier, like raising a number to a power, you just use 2 asterisks. Simple, clean, and powerful. Okay, so we have these abstract concepts. We've got our flexible lists, our labeled dictionaries, and these unbelievably powerful numbers. Now let's bring it all together and see how they solve that real-world car problem we started with. So here's our challenge. To test a car's safety systems, like automatic emergency braking, engineers need to run thousands of simulations. And for that, they need data. A lot of data. Specifically, they need to generate lists of random vehicle speeds to feed into that simulation. And the logic to do this is just beautifully simple. First, we import Python's random library. That's like grabbing the right tool from a giant toolbox. Next, we create an empty list to act as our container. Then we just tell the computer to loop 10 times. In each loop, it generates a random number, scales it up to a realistic speed, and then just drops that new speed right into our list. That's it. And this shows you exactly what you get. After you run the script, you end up with a whole range of different speeds. You might get a high speed like 210 kilometers per hour, a normal cruising speed like 122,
Or maybe a really slow speed, like 16. It's exactly the kind of varied, random data that a simulation needs to be truly effective. And here it is, the final result from our script, a Python list holding 10 random vehicle speeds. We started with a simple idea, and now we have a concrete piece of data that's ready to be used in a complex automotive simulation. Pretty cool.
So, we've gone from these abstract object types all the way to a practical list of numbers. But what's the big takeaway here? Why does a simple example like this actually matter so much?
And this is really it. Python's power doesn't come from being complicated. It comes from having simple, flexible, and powerful building blocks, like lists and numbers, that you can combine to build solutions for incredibly complex problems, whether that's in car engineering, scientific research, or financial analysis.
And that's the thought I want to leave you with. We've just seen how a few lines of code can model a small piece of the physical world. It really makes you wonder, if we can do this for a car's speed, what other systems, what other ideas, what other futures can we simulate and build with these same simple tools?